Welcome to the next lecture on stress in cylinders and spheres. What is Lame's equation for thick walled cylinders? The radial stress sigma r is equal to A minus B by r square. So, what is A and B? A and B are constants determined by the boundary conditions of the cylinder, internal and external pressures, and the internal and the outer radius. So, here if you see, we have clearly written it, right. So, these are the pressures which are acting, these are the radius, these are the pressures. So, P1, P0, and this is how the stress gets distributed within the material. R is the radius from the center of the cylinder. The constants A and B are determined by using boundary conditions of the cylinder, specifically the pressures applied at the inner radius Ri and the outer radius R. So, inner radius is this, outer radius is this. So, the circumferential, this is radial, the circumferential stresses are sigma naught is nothing but A plus B by R square. So, the difference, please note down the difference and please note down the radial stresses. So, through this you can try to find out what are the radial stresses and circumferential stresses for a thick cylinder. When at R equal to R1 inner radius, the radial stress is equal to the internal pressure Pi. So, you should read it like sigma R by R is equal to Ri, which is nothing but Pi. Okay. So, when the outer radius, when R equal to R naught, the radial stress is equal to the external pressure P naught, which is R sigma R by R is equal to R naught P naught, and this is how the equation is. Solving these two equations simultaneously allows us to determine the value of A and B, which can be used to calculate the radial and the circumferential stress at any point within the cylinder. So, this is for a thick cylinder case. So, we saw for thin cylinder case. So, this is for thin cylinder type, and here what we are trying to solve is for thick cylinder type. This is Lame's equation, which is also very important used in thick wall cylinders. Now, let us try to solve a numerical using the thick wall cylinder formulas. So, calculate the radial and the circumferential stress for a thick walled cylinder whose internal pressure Pi is given, external pressure P naught is given, then we have inner radius 0.1, outer radius 0.2, the radial distance is 0.15. So, what we are trying to say is this is inner, this is outer, this is inner radius, this is again this is outer radius, and the radial distance is R, right. So, that is what is 0.15, point where stresses to be calculated. So, what are we supposed to do? Determine constants A and B using boundary conditions. Which is O at R equal to R1, where the inner radius sigma R equal to Pi. So, A minus B by R1 square equal to Pi. A minus 100B is equal to 5. So, this is equation 1, and here A, this can be written as A minus B divided by 0.1 the whole square which is 5 megapascal. So when we try to solve it, A minus 100B is equal to 5 becomes the first equation. So now O at R equal to R naught, where it is outer radius. We are doing it for inner radius and we are doing it for outer radius. So that is sigma R equal to P naught. So A minus B by R naught square equal to P naught, which is nothing but A minus B by 0.2 the whole square equal to 0 MPa. So which is nothing but A minus 25B equal to 0 or A equal to 25B. This is equation 2. Now from 1 and 2, from 1 and 2 equations, substituting within them, it is nothing but 25B minus 100B equal to 5, which is nothing but minus 75B equal to 5. So which is B equal to minus 1 by 15. Now when we try to calculate A, which is nothing but 25 into minus 1 by 15, B equal to minus 1 by 15, and then you start substituting B in A. We try to get A equal to minus 5 by 3, which is nothing but minus 1.67 MPa. So by doing so, we are able to calculate what are the radial and circumferential strength for a thick wall cylinder. So from here, if you want to calculate the radial stress, calculating radial stress, sigma r at r equal to 0.15 meters. So the formula is sigma r equal to A minus B by r square. So where in which you substitute A and B value, which is minus 1.67 minus of minus 1 by 15 divided by 0.15 the whole square, which is equal to minus 1.67, and when you try to solve all these things, it comes to plus, minus of minus multiply, that becomes plus 2.96, which is nothing but 1.29 megapascals. This is the radial stress after finding out A and B. Now if you wanted to find out the circumferential stress for a thick wall cylinder, circumferential stress, which is nothing but sigma naught at r equal to 0.15 meters, we have sigma naught equal to A plus B r square, which is nothing but minus 1.67 plus bracket minus 1 by 15 divided by 0.15 the whole square, which is minus 1.67 minus, because plus into minus minus 2.96, which is approximately minus 4.63 MPa. So the radial stress at r equal to 0.15 equal to 1.29 MPa. The circumferential stress at r equal to 0.15 meter is equal to minus 4.63 MPa. So in this problem, we try to solve, find the radial and the circumferential wherein which we used this Lame's equation in finding out the radial stress and circumferential stress. The constants A and B has to be found out. We are trying to find out the constants and we are trying to solve the problem. Now, let us move into spheres application. Spheres application is predominantly found out in gas storage tanks. The spherical tanks are used for storing gas under high pressure, such as liquefied nitrogen gas or liquefied petroleum gas. So, you can see there all these gas storing tanks will be spherical. So, it will be rested on cylinders and then you form a sphere. Right? The spherical shape provides uniform stress distribution along all the directions, which minimize the risk of structural failure under high pressure. The examples we have already seen used in plants. When we talk about other applications, submarine hull is also a spherical one. The hull of a submarine are often designed with a spherical section to withstand the immense pressure exerted under deep sea. The uniform stress distribution in spherical sections of the hull enhances the submarine's ability to endure deep sea pressure, because in sea, when the hydrostatic pressure, there will be uniform pressure around. Now, you have to maintain this pressure. You are going inside water, pressures are going very high. With respect to height or depth, if you go, the pressures are very high. Then you will have to counter this fellow. Otherwise, what will happen? It will get deformed. So, spheres are very important to be considered when we are trying to talk or think about underwater. So, the pressure resistance compartment in the deep diving submarines are always used. The importance of uniform stress distribution, this always helps to maintain the structural integrity. In a spherical vessel, internal pressure induces stress that is uniformly distributed across the surface, reducing the likelihood of localized stress concentration that could lead to structural failures. Many a times when we start doing machining of a brittle material, right, machining of a brittle material like glass. So, what we do is we always try to take it inside a chamber wherein which there is uniform stress distribution around the piece. So, there will be pressure at this point of the workpiece, this point of the workpiece. When I try to machine, what will happen is it will try to convert the brittle fracture into ductile fracture. So, when you are trying to work on silicon machining, by chance you are trying to work on a single point cutting machine, then it always depends on that stress distribution. We are establishing a new facility at IIT Kanpur on hydrostatic machining operations. So, wherein which the cylinder will be made, inside a cylinder pressures will be exerted, the workpiece will be kept inside the cylinder such that we get uniform stress distribution. The efficiency in material use, the uniform distribution of stress allows for more efficient use of material, such as the thickness of the vessel can be optimized to provide sufficient strength without excess weight. So, you do not have to put a thick cylinder, rather than that we put a thin cylinder and we apply pressures uniform. Then the next one is safety. The uniform stress distribution contributes to the overall safety and reliability of the structure. So, for structural integrity, for efficiently using material and for safety, we always try to do this thin wall and thick wall calculations, and we try to maintain uniform stress distribution. Again, in sphere, you have thin wall and thick wall. So, thin walled spheres, the wall thickness is small compared to the radius. The wall thickness T is smaller than the radius R of the sphere. It has to be extremely small as compared to that of the radius. uniform internal pressure. The internal pressure P is uniformly distributed across the inner surface sphere. So, when we try to take a section, you will see here, this is sigma 1, sigma 2, sigma r. The elastic material, the assumption, elastic material of the sphere follows the Hooke's law. So, Hooke's law, what is Hooke's law? Hooke's law is, we can try to stress by strain, Hooke's law. Okay, this is strain, right? Okay, the isotropic material property, the material property are uniform in all directions. When we try to use a homogeneous material, we always try to simplify the calculations by using isotropic material property. So, let us try to derive or write down the equation for hoop stress or the circumferential stress in thin walled spheres. So, it is expressed as hoop stress is sigma h is nothing but P times R divided by 2 times T. So, if you have a sphere of uniform cross section, then this center to the mid of the wall becomes R. Then you see this one is sigma theta, this is T. So, sigma theta or sigma h is nothing but P into R by T, where P is the internal pressure. And for axial, sigma axial, longitudinal axial, it is going to be P times R divided by 2 times T. So, where sigma h is the hoop stress acting along the surface of a sphere, then P is the internal pressure and R is the radius of the sphere, then T is the wall thickness, Now, the formula of the hoop stress in the thin wall sphere is derived under the assumption that the wall thickness is extremely small as compared to that of the thickness. So, now let us try to calculate the hoop stress for a thin walled sphere, wherein which the data given are internal pressure P is equal to 1 MPa, radius R equal to 0.5 meters, the wall thickness T is equal to 0.01 meters. So, the hoop stress, which is going to be calculated as P times R divided by 2T. So, which is given by P is 1 MPa into 0.5 meters divided by 2 times 0.01 meters. So, which can be done in the same way, 1 into 5 into 100 divided by 2 into 1 into 10. So, I multiply, so that I remove. So, it becomes 0.1. So, it is 1. So, it goes away. So, it is 150 MPa divided by 2 times, which is nothing but 25 MPa. So, the hoop stress will be equal to 25 MPa. Okay. So, now moving forward, what is the assumptions for a thick walled sphere? The assumptions are non-negligible wall thickness. The wall thickness is significantly compared to the radius of the sphere, making it important to account for in-stress calculation. Next is, it follows Hooke's law. It has uniform material property. The internal pressure and the external pressure, the sphere is subjected to internal pressure as well as external pressure. the symmetry is also followed. So when we try to calculate the thick wall sphere radial stress, it is the same calculation like whatever we did like last time, pi ri cube minus p0, because there it was square and here it is cube. For a cylinder square, for sphere it is a cube. So r cube it is there. So now r1 and r0 are the internal and the outer radius of the sphere. R is the radius distance of the center. When we calculate the circumferential strength, it is the hoop strength sigma naught. So here we will try to calculate it in this using this formula, where Pi is the internal pressure, P naught is the external pressure. If the external pressure is the atmospheric pressure, then P naught all goes away. P naught goes away. So the stress distribution in a thick wall cylinder can be calculated by the radial stress is nothing but P suffix I, Ri, which is inner, and then outer, inner minus outer divided by the radius into R naught by R3 minus 1. So internal pressure, external pressure, inner radius, outer radius, and radial pressure. Outer radius, if it is atmospheric pressure, so we should be calculate of P naught. When we try to calculate the hoop stress for a given material, so it is calculated by this formula. The difference you should see, it is minus 1, this here it becomes plus 1, rest all is it is the same. So R naught cube, it is only this value it changes, R naught divided by small r cube plus 1 and minus 1. When we talk about hoop, it is plus 1. The radial stress decreases with the internal surface to the external surface of the sphere. It is highest at the internal sphere. So stress, so that's why we do a calculation, it always be representative. So the stress at this point is higher as compared to this point. So this is inner and this is outer. Here also you can represent it in a exponential function. Inner surface to the external surface of the sphere, it is highest at the inner radius and reduces to the external pressure at the outer radius. The circumferential, so it is interesting, in a sphere radius is 1, circumference is 1. So let's be little careful when we do the circumferential stress, is typically higher than the radial stress and reaches its maximum value at the inner surface of the sphere. This stress is a result of internal pressure trying to expand the sphere. So you have circumferential stress, radial stress. This is how you calculate the radial stress. This is how you calculate the circumferential stress. So where is it exhaustively used? We use it in pressure vessels in the design consideration. It is focused on material selection, accurate stress analysis, proper wall thickness and factor of safety to ensure the vessel withstands the pressure and operating efficiency. The temperature impact is also high. The material must handle high or low temperature without failure. There are several industrial standards which are there. ASME BPVC is a standard which is used for pressure vessel design. ISO has a pressure vessel design equipments, it is separate. Then API is specific for petroleum industry. EN 13445 and PD 5500 is the European and UK standards for unfired pressure vessels. So let's take a case study. The case study for our discussion will be a pressure vessel used in a chemical plant ruptured due to unexpected internal pressure builds up. The post-failure analysis reveals that the wall thickness was insufficient to handle the peak pressure during operation. So same way, when you take a balloon, you keep on blowing a balloon. After a certain pressure, what happens is the internal pressure is quite high. The wall thickness is very small. It pushes the wall thickness. At one point of time, the balloon bursts. So in the same way, this is a common failure which we always see in pressure vessels. So the internal pressures are very high. The wall thickness is very low. So the lesson learned from this case study is the failure highlighted the critical need for precise stress analysis and appropriate safety factor in the design phase. Inaccurate calculations or assumptions can lead to catastrophic failure, emphasizing the importance of adhering to industrial standards and rigorous testing protocol. So, predominantly what happens when we talk about a sphere, we try to talk about the radius and the wall thickness. This too is very, very important, T, and here the internal stresses whatever it is getting built. To recap whatever we have seen in this lecture, what is the primary purpose of studying stress in cylinders and spheres? How do you differentiate between thin wall and thick wall cylinders? What are the formulas used to calculate the hoop stress in thin wall and thick wall? What are the important parameters? How does longitudinal stress in a thin wall cylinder differ from a hoop stress? What are Lame's equation for thick wall cylinders? We underwent a numerical study. Then we saw the stress distribution for a thick walled sphere. Then a numerical problem was solved. Finally, we saw a real case study wherein which failure has happened in a pressure vessel. The importance of internal pressure getting developed. Wall thickness are very important when we try to work on either cylinders or spheres. These are the references which we have used while preparing for this lecture. Thank you very much.